Hello everyone. So today I'm here to speak on semaphores. Before I explain about semaphores in OS, I'll explain to you what semaphore actually means. So sema in French means a sign or a signal and phore means a conveyor. So semaphore is something which is used to convey a signal or something. So when it comes to OS, we'll see what are the uses of semaphores. So semaphores are used in processes where in multi-programming systems where process synchronization happens. In this process synchronization problems, we go under critical section problems. The critical section problems are problems where a process tries to access a shared data. When a process has its own private data, it doesn't depend on any other conditions. It accesses its own data and it goes out of the critical section easily. But when it comes to shared data, the process tries to access the shared data, and suppose the shared data value is changed, then the process goes into critical section, which results in a deadlock and the problem cannot be solved further. So there are three criteria which have to be ensured to make sure that the race condition doesn't happen. That is mutual exclusion, progress and bounded width. So mutual exclusion is the principle where only one process can enter the critical section at one particular time. Progress is, suppose there are n processes, it's not necessary that each and every process has to go into the critical section. The problems which are actually necessary to enter the critical section, those are the processes which go. And bounded width is like you have a width and a process can make only that number of requests to the operating system to perform its request. So semaphore in operating system is just a normal integer variable. It is used to access a common resource in multi-programming systems. It decides the order of execution of processes and how it manages the resources. So in semaphores there are two operations. That is P and V. The P operation is also called as the wait operation and the V operation is also called as the signal operation. So this is an example. Now to explain this example, I'll consider a situation. Suppose we are in a restaurant and the maximum capacity of the restaurant is 50. So the semaphore will be assigned as 50. And when a person enters, the semaphore will be decremented. So the deadlock situation will occur when the complete restaurant is filled with 50 people and no number of people nobody else can enter inside. So the people outside waiting must wait for the semaphore to finish its job, that is for the person to finish eating and to go out of the restaurant. So when the person goes out of the restaurant, the value of the semaphore will be incremented, that is a place in the restaurant will be empty. So the other person can go. That is the operation of P and V, which is P says wait and V says you can access the data. So as we all know, semaphores are used to solve critical section problems. And we also know that operating systems has a lot of classic problems like the producer-consumer problem, the reader-writer problem and the dining philosopher's problem. So to explain about semaphores, I am gonna take the producer-consumer problem. When in the producer-consumer problem, when you don't use semaphores, this is a situation that occurs. So when we assign the value of item count as 0, the consumer block will start its execution. It notices that the item count is 0 and then the producer is awakened. So when the producer comes, the item will be added into the buffer. After adding the item into the buffer, the producer tries to wake up the consumer. But since the consumer is already working, the consumer goes to sleep because of the because of the loss of wake up call by the producer, and then the consumer goes to sleep. So the producer produces items into the buffer until the buffer is full. So when the buffer is full, the producer also goes to sleep. Hence, both the producer and the consumer both are in sleep situation, which occurs in a deadlock because none of the processes are actually working. So using semaphores, so using semaphores, here I am going to use 2 semaphores. So I have used 2 semaphores which have fill count and empty count. Fill count will give you the number of items that are being produced, and buffer count will give you, buffer size will give you the remaining space in the buffer. So using the same thing, I am going to explain you when the producer, in the producer block, so consider the producer block. I have given 2 semaphores which are fill count and empty count. So when in the producer block, when the producer starts working, it notices that the fill count is 0, so the buffer size is automatically 0, so it produces an item. When it produces an item, the buffer size will be incremented. So when the buffer size is incremented, the consumer block starts working. In the consumer block, we'll make sure that the consumer is sleeping as long as the producer is giving the items into the buffer. So when the consumer is up, the producer goes to sleep, and hence the value of the empty buffer size will be decremented. That is like suppose empty count, take the same example, suppose the restaurant has 50 people. So when you come, the restaurant, it's 50, and then one person is entered, so the buffer size will be 1 and the fill count will be 49. So you add the number of people and the consumer works with respect to the producer in this. So we can say that semaphores actually solve the critical section problems and also make sure about the mutual exclusion, since only one process can work at a time. This is about semaphores. Thank you.